linear algebra. To me, if I was forced to pick the best course available for somebody who will get into and do a little bit of technical stuff, but the best course that I have seen is linear algebra, because it permeates through everything, and it's the music of data science. So here you have, this is, I'm going to be forced to write things, but so matrices, okay? First of all, we use uppercase letters such as A, B, C for matrix, to name matrices. And a matrix has rows and columns. So if you have something like this, 2, 3, 4, 5, 1, negative 1, 0, 2, okay? We use notation like that. So there are 2 rows. So if I use A equals to, so A is 2 by 2 rows by 1, 2, 3 by 4 columns. All right? And it's very important to know that. So if I have a matrix, if I have this matrix A, right? So this is, and I have another matrix B, 0, 0, 1, 0, 1, 2, 3, 9, then I can add them. So A plus B, right? In order to do the addition, they have to have the same dimensions. So A is 2 by 4, and so is B, 2 by 4. So they have to have the same number of rows and the same number of columns, right? And you simply add the corresponding elements. This is 0 plus 2, so that's 2, right? 0 plus 3, 3. 1 plus 4 is 5. 5 plus 0 is 5. 1 plus 1 is 2. Just add the corresponding elements. Negative 1 plus 2 is 1. 0 plus 3 is 3. What did I put here? Let's make that 2. 2 plus 9, 11. Right? Not difficult, right? That's the addition. Now, if I do A plus B, it's the same as doing B plus A. Right? So this is called addition is commutative. A plus B is B plus A. If I subtract, once again, with the subtraction, the dimensions have to be the same. So it would be 2 minus 0 is 2, 3 minus 0 is 3, 4 minus 1 is 3, 5 minus 0 is 5, 1 minus 1 is 0, negative 1 minus 2 is negative 3, 0 minus 3 is negative 3, 2 minus 9, negative 7. So that's subtraction. Right? I just want to cover some basic things. But b minus a is not commutative. B minus a is not the same as a minus b. Right? It's clear. But b minus a is 0 minus 2, negative 2. Okay? 0 minus 3, negative 3. 1 minus 4, negative 3. 0 minus 5, negative 5. So it's the negative, right? 1 minus 1 is 0. 2 minus negative 1, that's 3. All right? 2 minus negative 1. 3 minus 0 is 3. And 9 minus 2 is 7. All right? So basically, you see that this is the negative of that. Okay? Let me just take a look and see how far I can go. This will grab it. Okay. I can also do 3 times a, multiplying a constant. Right? This is called scalar. We'll try to write big. Okay? So 3 times a, you multiply everything by 3. All right? So it would be 3 times 2, 3, 4, 5, 1, negative 1, 0, 2. And so this is 6, 3, 9, negative 3, 12, 0, 15, 6. Right? And this could be negative 3, it doesn't matter what the number is. So m will be the number of rows. M is the number of rows, n is the number of columns. If m equals to n, then we have a square matrix. So if you have, let's say, a 2 by 2 matrix, that would be something like 7, negative 2, 4, 4. 2 rows, 2 columns, or 3 by 3 or 4 by 4, right? Okay. So this is matrix addition. We talked about matrix multiplication. I'm sorry, not yet. Matrix subtraction, multiplying a matrix by a constant, by a scalar. So if I have a matrix, let's say E, and it's 0, 1, what are the dimensions here? How many rows? 1. So this is 1 by 2. What about if you have this matrix? What is this? 1 by 1, right? So the number 1 you've been using all your life is a matrix. So you have been doing matrices. Everything is a matrix, right? So 2 is a 1 by 1 matrix. Matrix 4, when is that coming out, the movie? You guys don't know? You have to watch it. It's all AI. it's all linear algebra. When he stands at a certain angle, they use things to support that you don't see, but it's all linear algebra behind the scenes. So if you have a column like this, right? This is a one-column matrix, so that would be 4 by 1. Okay? Or this could be 2, 4, 5, 4. This is 1 by 4. So this is 1 by 4. In fact, when you take, if you have, well, we'll talk about the transpose. This is the transpose of that. But I'm going to talk about it in a few minutes. I will give you the basics that will allow you, though, to be able and follow a lot of material. A lot of times you will see if I use this or the parentheses, same thing. All right. So if you have a matrix M that has 2, 3, 5, 6, right? Negative M is, you just apply the negative to everything. So let's say this was a negative, right? So it would be negative 2, 3, negative 5, negative 6. So this is the same as negative 1 times M. Everything that you do in real life will involve matrices. Everything. Okay. We need to have some basic understanding, because I want to show you the Mahalanobis distance, the statistical distance, which is used behind the scenes with discriminant analysis. Okay. So if you want to, you're welcome to take pictures of what I'm writing. To save time, you can use your smartphones. Okay. So we did matrix addition, subtraction. Let's talk about multiplication now. To multiply, and I have to remind myself to write big, two matrices, A, N by two matrices A and B, okay? The number of columns of A must be equal to the number of rows of B. So in other words, A, if A is n times n by m, we use m for rows. If A is m by n, and this is multiplied by B, B has to be n by r. These two have to be the same. The other two don't. And the result, C, will be m by r. So let's do an example. If I have A equal to 1, 2, 3, 4, 5, 6, I'm making up these numbers. So A is 3 by 2, right? And B has to be 2 by something. So B can be, let's say, 2 by 6. So this could be 3, 3, 3, 2, 2, 1, negative 1, negative 1. I'm just picking easy numbers, all right, like that. So A times B, so A times B, so A is 3 by 2, and B is 2 by 6. So you can do the multiplication because the number of columns of A is equal to the number of rows of B. So this is 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 2, 2, 1, negative 1, negative 1, negative 2, negative 3, negative 1, 0. And the way you do this is you take the first row and multiply it times the first column. And you see the dimensions have to match because you have 2 here, you have to have 2 here. So you have 1, 2 times 3, 1, right? So this is, I'm going to do this once in a lot of detail. So that would be 1 times 3 plus 2 times negative 1. This times that. Okay? And it gives you this. And this will be 3 minus 2. That would be 1, right? Okay. This will take, we need some space. But I'm going to do a few. So then you multiply the first row times the second column, the first row times the third column, like that. So then you'll have, the next one would be, oh, I have the same thing. 3, okay. Then the next one will be the same. 1 times 3 plus 2 times negative 1, right? So first row times the second column. Then the first row times the third column. 1 times 3, 1 times 3 plus 2 times negative 2, right? And remember, this is, you're using parentheses here. You have to be careful, right? So this is 3 minus, so that's a 1. This is same thing, 1. This is 3 minus 4, negative 1. Then you'll have 2 minus 6, negative 4. Then you'll have 2 minus 2, 0. 1 plus 0, 1. So once you're done with the first row times the first column, second column, third column, fourth column, fifth column, sixth column, you get these numbers. Then you go to the second row and you multiply the second row times the first column, the second row times the second column, blah, 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 right? So you'll have 9 minus 4 is 5. Same thing here, 5. Then you'll have 9 minus 8, 1. 6 minus 12, negative 6. 6 minus 4, 2. And 3. Okay? So then you have this, right? So if you have, if A is 3 by 2 and B is 2 by 6, the result, see this with that, they have to agree to agree, and then the result will be 3 by 6. So then you take the last row times the first column, last row times the second column, like that, right? So this is 15 minus 6 is 9. 9. 15 minus 12 is 3. 10 minus 18, negative 8. 10 minus 6 is 4, and 5. Okay, this is the 3 by 6. Okay, so you can actually do this, all of this in Excel on the TI, but it's good to know the you know what is going on, what is happening. You see, you can do A times B. If you tried to do B times A, can you do this? Are these two the same? No. So this cannot be done. Not this Thursday, next Thursday, the test will include this. So if I give you something like this, and you come up and you ask me, but this cannot be done, I will say, I can't help you. The answer is cannot be done. All right? There's no division of matrices, okay? At least so far, there's no division of matrices. I mean, yeah. But I've done this example in a lot of detail. So, addition, matrix addition is commutative. This is a nice word to know because you'll hear it a lot. Commutative, matrix addition is commutative. It means A plus B equals B plus A. Matrix subtraction is not commutative. A minus B is not the same as B minus A. Matrix multiplication is not commutative because A times B, right? Generally speaking, A minus B does not mean that you can do B times A. That you can do B times A. Okay, let me know. This is basic, very basic linear algebra. I've been wanting to do this class for business students here. I taught this course in a community college, linear algebra, and it's just an amazing class. It's a class where you have to work extremely hard, but the dividends are extremely high. So if you want to be in data science and do more in analytics, take a course in linear algebra. Okay. So that's that 9.1, and it has exercises at the end of this section in that document. Okay. By the way, I told you about my sister had a friend, this tiny, short Chinese girl, and that she was making $250,000 starting salary. Well, I was talking to my sister about Lucy. I lied to you. She made $450,000, and she retired at the age of 40. She was very good with numbers, and my sister was telling me, it was actually Sunday, how this girl was so good with numbers, she was telling her bosses, buy this stock, for 30 cents on the dollar, and the company kept ignoring her, and when they end up buying the stocks, they would pay 90 cents instead of the 30 cents that she was telling them. Lucy actually told my sister to invest, and my sister did not do it. If she did, she would have made millions of dollars. And so Lucy told her boss, I am quitting. And then her boss's boss, the big person, went and told her, how much can I give you to keep you? And she told him, nothing. And she left, and she had enough money. And before she was 40, she retired. And she was handling the investments of her family. Her husband also worked for Oracle. They were both making very good money. And so, but she was very good with numbers, and she knew what she was doing. So within a year or two, when she made her company tens of millions of dollars. And when they see somebody like that, they reward you. She was making $450,000 within a few years when she was working. And this is what I'm trying to tell you guys. If you listen to what I'm telling you, you can do that. So, as I showed you, you have all been using matrices. When we do regular arithmetic, 1 times 5 is 5. 1 times anything, right, is that number. So the two numbers that impact what we do a lot are 1 and 0. The number 1 is a matrix, 1 by 1, 1 row, 1 column. In matrices, we have I, the identity matrix. The identity matrix. Excuse me. So if this is 2 by 2, this is 1, 0, 0, 1. So the ones have to be on the diagonal this way, not the other way. 3 by 3. A 3 by 3 identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. The ones have to be in the diagonal this way. And this is used a lot because many times they talk about this upper diagonal or the lower diagonal part of the matrix. If you have any matrix A, so let's say A is A, B, C, D, any numbers. What do you think A times I will be equal to? Look, instead of A, use 5. What is 5 times 1? 5. A times I is A. So look, if I put A, B, C, D, and I multiply, by the way, the identity matrices, even though there's some other things, for us, they are squares, all right? If you do this multiplication, A times B times this, if you multiply this times that, that gives you A, right? A times 1 plus B times 0. If you multiply this times that, that will give you A times 0 plus B, that's B. CD times 1, 0, C plus 0, C. And CD times that will give you D. Also, if you do I times A, you will again get A. Okay, so the same thing, 1 times 5 is the same as 5 times 1. Okay. So that's important to know. The if A equals 1, 0, 0, 1, A or I, this is 2 by 2. what do you think? Well, I square would be I times I. This will be equal to what, do you think? I. The same thing as 1 squared is 1 times 1, right? This will be I. So multiply 1, 0 times 0, 1 by itself. This times that will give you 1. This times that will give you 0. This times that will give you 0, because 0 times 1 plus 1 times 0, and this times that will give you 1. So in fact, I to the n power, I to the k power will be I. 1 to any power is 1. Okay. The next thing that I want to talk to you about is the two things. One is the inverse of a matrix. The inverse of a matrix A. All right? 1, A must be square. Even if A is square, this does not guarantee that A has an inverse. But A must be square. Then let's say that A, this is called the inverse of A. And it looks like A to the negative 1, but this is called the inverse of A. The inverse of A. If A has an inverse, A like that, right? Then A times the inverse must be equal to the identity. And if A has an inverse, okay, like that, A times the inverse equals the inverse times A, and they're both equal to the identity matrix. So I want to show you an example of how we find the inverse of a 2 by 2 matrix. This is very, very important. I mean, the time for this course is needs to be spent, needs to be used very, very efficiently. And this is extremely important for everything. So 2, 3, 1, 2. Here's the question. Find the inverse of M equals 2, 3, 1, 2. Okay? 2, 3, 1, 2. Okay. M is square, all right? So that's a good thing. But just because M is square, that does not guarantee that we will find the inverse. If you have an inverse, A must be square. Always. if A squared or M is squared, that does not guarantee that it will have an inverse. So, so M is squared. So we know that if M has an inverse, okay, like that, and let's call the inverse A, B, C, D, anything. The following must be true. The following must be true. M times the inverse must be equal to I. Now all of these are 2 by 2, 2 by 2, 2 by 2. So we have 2, 3, 1, 2 times A, B, C, D. This must be equal to 1, 0, 0, 1. Right? M times its inverse must be equal to that. Okay, so do the calculations. 2, 3 times AC, that gives us 2A plus 3C. Let me write it here. Let me save space. 1, 0, 0, 1. So that will be 2A plus 3C, then 2B plus 3D, 2B plus 3D, then 1A plus 2C, 1A plus 2C, and 1B plus 2D, 1B plus 2D. Right? You see that, right? So that means this 2A plus 3C must be equal to 1. 2A plus 3C must be equal to 1. And 1A, so A plus 2C must be equal to 0. 2B plus 3D must be equal to 0. And B plus 2D, B plus 2D must be equal to 1. I'm sorry, no, hold on. Yeah, hold on. This is 1, this is A plus, so this must, so you are doing this equal to that, this equal to that, this equal to 0, and this equal to 1. Yeah. So here you have two equations, two unknowns, very easy to solve. Okay, so from this, you have A equals to negative 2C. So you go to the first one, 2 times A, 2 times negative 2C, plus 3C equals to 1. So this means negative 4 plus 1, negative C equals to 1, therefore C equals to negative 1. I just want to make sure that I will get. This is all in the document. So C, A, B, yeah. So that's C. Well, A is negative 2C, which is negative 2 times negative 1, or 2. Similarly from here, you have B equals to 1 minus 2D. You go to the first one, 2B, and you have 2 minus 4D plus 3D equals 0. So you have 2 minus D equals 0. Hold on. Yeah, okay, so you have D equals to 2. And so B equals 1 minus 2 times 2, or negative 3. So, if I did my calculations correctly, so we have the inverse is A, B, C, D, okay? Let me write it below. This is the inverse, A, B, C, D. So I got 2, -1, -3, and 2. I think that's correct. Well, so the question is this the inverse? Okay, so proof that this is the inverse, if I multiply m times the inverse, I better get this. So let's multiply m, 2, 3, 1, 2. This is m. The inverse is 2, -3, -1, 2. You see there's some funny relationship between these. So if you multiply 2, 3 times this one, this will be 4 minus 3 or 1. Then this times that will be -6 plus 6 or 0. 1, 2 times this will be 2 minus 2, 0. And this times that 3 minus 4 or 1. So then you say 2 minus 3, -1, 2 is the inverse of m. This is the proof because m times its inverse gives you back the identity as it should. All right? So this is very important, and of course you don't do this out, you have the software do it, but it's good to understand the process a little bit, right? So if you have a 3 by 3, you're going to have a lot of, this is called the system of 2 equations and 2 unknowns. 2 equations and 2 unknowns. And the system had a solution. See, if this does not have a solution, you don't have an inverse. Okay. The last thing that I want to talk about is the transpose. And all right. So the transpose of a matrix A turns rows into columns and columns into rows. So if A is 2, 4, -1, 0, 5, 9, 6, 2, okay, then the transpose of A will be, you turn this row into a column. 2, 4, -1, 0, 5, 9, and 6, 2. Okay? So it's that simple. That's it. So we erase this. What you have just seen, okay, in less than an hour, is actually enough to be able to understand a lot of articles that do not use sophisticated linear algebra. Linear algebra can get very, very theoretical. But the more of it you understand, the better off you will be. Okay. So everything that I went over is in that TM week 9 whatever. And all right. And you will see how, you see, this is the formula for the Mahalanobis distance. I will, this is what discriminant analysis uses. So here is the transpose of this times the inverse of this is the covariance matrix times this. This is all matrix notation in bold. So that's the statistical distance. Okay. Let's talk a little bit about, in fact, I'm going to open the part. I found somewhere, where are my PowerPoint slides? Okay, this is chapter 12 in the Smueli book. Okay, these are the PowerPoint slides, that's the latest. And okay. So, discriminant analysis has been in existence for a long time, and it's used very heavily to classify species into, like, you know, when you look at the taxonomy, they have two-legged animals, four-legged mammals, non-mammals. Classifying skulls is used extensively to find criminals. Or for fingerprint analysis. It's used a lot in loans, profiling customers. Okay, profiling is when somebody looks at your general characteristics and they say you are from that part of the world. That's profiling. It's used. You know, we hear the terms racial profile, but you look at an observation and you make a general assumption. An example that I'll show you a small example today, and I produced a big document that has all the steps in JUMP as to how to do it, and JUMP is actually very good. So you want to classify bio or non-bio of riding mowers. So we will have this file. Let's look at the file right away. This credit approval table. Let's see. I told them to fix 14.2. Let's see if they did it. What version is this? Okay. All right. So this is the data file. All right, this is the data file. these records highlighted like that? I don't know. Look at the color. So this data, this will be generated. So let me remove all of this. Okay. You have people are applying for a credit card. All right. We have seen this data file with KNN. In fact, I would like to, after I do this with discriminant analysis, I like to do this with KNN quickly and then with discriminant and do a model comparison. Okay. So this data is not ready because you need to have homeowner needs to be with zeros and ones. We need to dummify the data. The same thing with the decision, even though some algorithms will take them as they are, and that's why I let me delete this. I don't have too much. That's why I have credit approval coded 1. So this is data cleaned up. There you go. So I have it in the right format. Let's remove this. So I used dummy variables, right? And the idea, this is actually, actual means it's the decision, the actual decision. 0, the application has been rejected. 1, it was approved. This is my data. So we have the outcome, okay? Let's see if I can have both at the same time. Okay. This is the outcome right here. Oh, this is not the riding mowers. I should have, this is the riding mowers. Okay. So, this is, so you have income, lot size, and you try to predict based on the income and the lot size, the lot, the yard in front of the house, if those two can be used to classify the person as a mower. You know what a mower is, right? To cut the grass. So you need to change this into, this is the data file though, and always know what the data file, what everything means. So we want to turn this into ones and zeros. Okay, that's the data file. Okay. And PowerPoint slides. I want to look at the latest. So you have two predictors. These two predictors. Now, this is owner is 0, non-owner. So this does not mean the 0 goes with owner. 0, non-owner. I mean, you can do whatever you want, but for us, 1 will mean owner and 0 will mean non-owner. Okay. All right. When you plot the data and you do a scatter plot between income and lot, and then you color things based on, we did this graph. And remember, I drew this line, all right? So you can draw this line to separate owners from non-owners. Another one, another example is the universal bank with two predictors. All right, I want you to know the data files that, and I should have that here. Universal bank. And People are applying for a loan. Here you have more columns. And the outcome is if you're going to get a loan or not based on these criteria. All right. And for now we're using, actually this is accept the loan or not accept the loan. And we choose to use only 2 of the main independent variables. You can, this file has 5,000 records. Okay. If you go to an interview and they say, we have huge files, you tell them how many records in the file. If they say 5,000, you say, this is so tiny, it is, if they say 5 million, insignificant. 5 billion, extremely tiny. So they say, so what do you think is a large file? It has to be exabytes, terabytes. These are big files. Okay, so the thing is that if you do, which columns? Annual income, if you do a scatter plot, if you take a sample of 200, okay, and you do a scatter plot, annual income and monthly credit card average. So if I go monthly income and, no, annual income and monthly credit card, always be aware of the units. So income is the income and the CCA is right here. So if I want to take a sample, where was that? In a table, I forget where we get the sample. Columns, utilities, no, rows, table. I think it's in the table. Anyways, if you get a sample and you plot it, you see there's congestion. And to make it so that the observations are not on top of each other, you will need to use jittering. If this is a problem with 200, if you use all 5,000, it will be extremely messy. Okay, so let's talk a little bit about the idea of what a discriminant analysis algorithm does. What you have is you have 2 classes, yes, no, all right? So you have this is everybody. This is everything. Right? This is the population. This is the population. The population will have a centroid. Centroid is not the same as the center. If you have observations, okay, and you find the average of the observations, let's say that this is your observations, okay, here. You have the 5,000 observations, all of them. The centroid, the average, may be here. So this is the center, and this is the centroid. I will show you how we can actually find this. It's very easy. This is the centroid, okay? Okay, now Here you have all the people that accept the loan, okay, that accept the loan so basically all the ones, and you have these observations right here, like that. And this class, class 1, right? Let's say the centroid of this class is here. So let's call this x1 bar. Then you have the other class, no accept, so these are the zeros, okay, not accept the loan, and these are your observations here, let's say, and this is your centroid right there. All right, this is your centroid. This is x0, sorry. This is a centroid. So, if I have a new observation, okay? So this is so this here, this is x0 centroid. All right? If I have a new observation, and the new observation is here, all right? You measure, in the beginning, let's use Euclidean distance. You measure this distance, let's call this distance from class 1, and then you measure this distance from class 0. And you assign this to the nearest class. So this should be assigned to class 1. Okay. This is using the Euclidean distance. Now, let me do this. The Euclidean distance, right? The Euclidean distance has some drawbacks. It does not look at the covariance and correlation. So it ignores covariance and correlation. And let me draw you a picture that you will be able to use that. So the discriminant analysis uses statistical distance, the Mahalanobis distance. And let me show you why. Oops. You remember when we talked about sensitivity and specificity? Here, we have two classes, right? We have class 0. We have class 0 and class 1. All right, and class 1. Look. This is the average of class 1. All right? Let's call this x1 bar. And here is the average of class 0. Now, if I take variance into consideration, x1 or the class 1 can have, if it has a large variance, the distribution can look like this. And this one can have a variance that is smaller. The graph is like this. Which means if the observation is here, if the new observation is here, right? If you use the Euclidean distance, you will assign this to class 0 because you don't, the Euclidean distance does not take into consideration the variance. But this can very well be part of class 1. You see? So, Euclidean distance does not cut it. When you have predictors that are highly correlated. So this is, remember, people that like, these could be people that like classical music and their interests have a large variation, and you can be here, right? You're physically close to somebody next to you who likes jazz, let's say rap music. If you use the Euclidean distance, you will be assigned to the rap group. Whereas if you use the relation, the type of music, you are assigned to classical music. So the statistical distance, okay, the statistical distance is named after an Indian fellow, Dr. Mahalanobis, and that is a big contribution to analytics in general. So this is the Euclidean distance. So you have the two classes. You set the centroids. If I have in two-dimensional, if I have a point here, let's say this is the point 1,5, okay? And I have a point here like 6,1. How do we find the centroid? How do you find the centroid? So the centroid is equal to, this is huge, the x-coordinate of the centroid is the average of the x-coordinates, so that would be 1 plus 6 over 2, 1 plus 6 over 2, and the y-coordinate is the average of the y-coordinates. 5 plus 1 over 2. Okay? And this is equal to 7 over 2, which is 3.5, comma 3. Okay? So the centroid is 3.5, 3, somewhere here. Okay, so let's approximate. So this is the centroid. 3.5, 3. Right? So that's the centroid, it's a dot here. So it doesn't matter how many dimensions you have in the 10th dimension space or 4th dimension space. If I had 1,5, 3, 5, right, 4-dimensional space, and this is 6,1, 4, 5, right, in 4th dimension, then you find the average of the x coordinates, the average of y, the average of z. So the third one would be 3 plus 4 over 2. Oh, again 3.5. And the last one would be 5 plus 5 over 2, or 5, right? So you just add, you divide by 2 the corresponding. And if you had more than, if you have more than if you have 4 points, or these 3 points, right, each in the 4th dimension, to find the centroid, you take 1 plus 2 plus 3 over 3, 5 plus 3 plus 3, right? Let's change these numbers. 6, 7, 8. Okay? To find the average in the third location with 3 plus 4 plus 7 over 3, like that, right? So that's how you find the centroid, very easily. All right? You see, when we try to find the Mahalanobis distance, right, you subtract the corresponding elements, and what you want to do is, for each point, so here is the centroid. So this is the center. The centroid can be right here, right? And this can be in n dimension, right? And so this is x1 bar, right? And here is the other centroid for this right here, and you have a point right here. So you draw the distance from this point to that centroid, right? So this is a point x1, x2, x3, xp. I just want to stick with the notation. P is the number of dimensions. So the Euclidean distance from here to here is, you take, okay. So the Euclidean distance, right, would be x1, well, this right here would have p numbers, right? So we found it. You take these square roots and you add them up. Let's say that this was 5, 9, 6, 4, and this has coordinates 3, 6, 4, 7, right? So the Euclidean distance would be what? 5 minus 3 squared plus 9 minus 6 squared plus 6 minus 4 squared plus 4 minus 7 squared, and then you take the square root of that. That's a Euclidean distance. Okay. Now, this formula does not take under consideration the variance, as I showed you when I showed you the bell-shaped curves, and the correlation. This formula, you see, well, this formula here, this is the transpose. You take these differences. This is using matrix notation. That's why it's in bold. This item in the middle is the inverse of the covariance matrix, and the statistical distance that it refers to here is what's called the Mahalanobis distance. I want to show you next time, well, I don't think we have the time today, an example of the Mahalanobis distance. Actually, let me try to see. Here I have an Excel file. I'm not going to, I want you to know what that is, but I'm not going to test you. I'm going to show you a little bit of linear algebra. So I have this data file here, which has this Gatling 2 data file, and I will quickly go through it. So here you have two columns. This is business age. This is the, I think, number of months that a business is operational. This is and the business has made a loan. This is the number of days that the company has been delinquent. Their payments are in arrears. And this is if they defaulted on the loan, yes or no. This is actual data. And what we want to do, if you have a new, how many of these do I have? 101, I think it's 100, I have 100 records, okay? I on purpose sorted them by the default, no or yes, okay? Let me go through the process of how this Mahalanobis distance is calculated. You have this example here. So I have on purpose sorted the data. This is very important to know the idea behind it. So I sorted the data. I have 75 nodes. So I have two classes, 1 and 2. One is represents, and you can add 0 and 1, it doesn't matter. One is for the people that do not default, and yes is the people that default. So I count, this is count if C2, right, through C101, how many are nodes? So it's 75. Then I calculate the proportion of, if I do the formulas, formula trace precedence, 75 out of the total is 100. And I find for those 75 records, so if I color them, coloring things at the right time is quite useful. So these are the records that where the outcome is known, the actual outcome. They didn't default. And this is with another color, the people that did not default. Okay, so what I do, I find the average of the bus usage business age. It's 116, right? The average of this column for the nose, for the yellow. And then the average for the delinquent days. So I have a mean vector. We call it mu1 here. That's what I called x1 bar. And you have two numbers, 116, 23, and 1689. And I can put the numbers this way, right? So this is my mu1 vector. It's a vector. This is a matrix with one column. It's called a vector. I do the same thing for the other class of people that did not default, and I have mu2. Then I actually this does something that I did not find in JUMP that it's doing, but okay, this item at the end delta, this is the Mahalanobis distance. So then I do mu1 minus mu2. So 116 minus 115 is 111. 16 minus 55 is this. This is mu1 minus mu2. What I do next is I see this right here is no. This should be yes. This should be yes. Yes. I need to fix this and yes. So I use color yellow and green, so that should be, don't worry about it. So that should be with the green. So what I do here, I find the covariance matrix, the covariance between business age and business delinquent, all right? And I show you how to do this here. I created this business usage N array, business usage, business. So the covariance between business usage and business users is the variance, right? So the covariance of x comma x is the variance of x. We went through this before. Then here I do the covariance between the business usage and the delinquent days, okay? And what I did was, if I take this column just for this, you see I gave it a name, right? And I did the same thing. This is business using N array. This is business using business age Y array, right? And I did the same thing for delinquent days. So here I'm trying to find out if I'm trying to find the covariance between matrix between this and that, and I call this C1. You can look it up how it's calculated. And I do the same thing here. I have C1 and C2. Then I create, you see this formula right here? 1 over N1 plus N2. N1 is 75, N2 is 25. I do these calculations, and based on what I showed you, you can do this. And I found, this was actually from, I got this I think from Said Sayad, that website. And then I have my pool covariance matrix. Then I find the inverse of this covariance matrix, which is this. And I use Excel to do that. That's the inverse. So I have mu1 minus mu2 from up there. I bring it down. Then this beta is the inverse times the difference, and you get this beta coefficients. I will show you where that is going to be used next time. And now you have z equal to these numbers times the columns. This is, we're going to use this next time. Then what I do, so this is, beta is these two numbers. And then you take the transpose of beta, so beta is negative. Oops. Okay, the transpose of this, negative 0.095 and negative 0.14. Okay. That's the transpose. And I multiply the transpose of beta times mu1 minus mu2. You get 540. And then you take the square root of that. That is the Mahalanobis distance. So what this says is that I'm not going to hold you responsible to calculate this, but I want you to know a little bit of what that is. Let's see if it's defined here. So, so if you have, as we do have the two classes, class 1, class 2, and this is the centroid of class 1, right? And here you have the centroid of class 2. Of the other class. I think here we had classes 1 and 2, yeah. And when you, the Mahalanobis distance is the statistical distance between those two. If this is what you want when you classify, do you want these circles to be like this or like that? Which one is better and why? Do you want the classes to have overlap, or do you want them to be separated like that? Which one makes it easier to classify? This is picture A or picture B? Picture A, because it's easier to classify when they are far away from each other. So if they are, it's easy to classify. See, if it's like this and you have an observation to be right here, which one are you going to assign it to, right? If they are far away, it's easier to classify as being something being on class 1 or class 2. I will repeat this next time, but I also want to show you. Let me take the riding mowers. Okay, we have a few minutes. I want, let me just do it manually. Okay, and change this to zeros and ones. This is the outcome variable. I want, because this is supervised learning, we have the outcome variable. So I want to create, anytime that supervised learning, you want to find the, create the validation column, and I have very few records, so 0.6, 0.4, 0. Use, it doesn't matter, I keep using this number. Call this, I would call this partition, oops. Okay, So here you get this, right? Now, one thing that you can do also is you can sort things by this, right? So you see these are my training records, and you can also pull them out and put them in separate tables, depending on what you want to do. Now, then I can go to multivariate methods, and I go to discriminant. That's where this is. Okay. Now, this is kind of it. The way they use X and Y, it's the opposite of what we are used to. The ownership has to be something that has this color. So if you go to the ownership, this is character nominal. It could also be numeric nominal, but right here. So you move this to the X, the income and the lot size, these are the covariates or predictors, they need to go to Y. This goes into validation. For now, let's just leave them the way they are. We have different types of discriminant analysis, linear, quadratic, and some other. Then I click OK. Okay, there's a lot going on here. Let me bring up, so here you have the, don't worry about entropy right now. If we have time, I'll explain what that is. You have the confusion matrix for the training and the validation. The validation one is more meaningful. Here you have some, so the training had altogether, how many records are in the training? We said 60% of 24, that's like, so you have 14, one was misclassified, so this is the percent of the misclassification. Don't worry about this other two. So you have a 40% misclassification in the validation, but again, we have a small data set, right? Now, up here, let's not worry about this. Up here, you can say, give me, in the score option, show me, here's the table. Okay, here's the table. I'm going to redo this. But show me the distances to each group. It shows the distances. Show me score and show me the probabilities. Show me score options is when you have new, so you want formulas. But look, if I say save formulas, right, then you will see some stuff to be added here. So if I say save formulas, here you have here you have a on the table. I'm going to explain what these are, but this square distance 0 is the Mahalanobis distance. If you want to find out what formula it used, you right click. I'm giving you enough so that you can play if you want to. You can see the formula. So this is the formula for the Mahalanobis distance, and this is a matrix here, the matrix that S. Okay, so here's the matrix and here's the covariance matrix. Okay, so anyways, I'm going to stop right here. I showed you a little bit. I'm going to start the whole thing from scratch next time. Have a great day. The quiz will be on KNN this Thursday, all right? So, is there something due today? Turn it in. Once you leave it over there, I have a lot of paper. I want to mix it up.